This semester I am taking 3 graduate level courses plus the measure theory seminar. The measure theory seminar, if you're curious, is an informal seminar among people that are interested in analysis. So they go to the seminar, they invite people from, all over the country, but also within the faculty, mostly within the faculty. But if they have visiting professors, they come in and give a talk on whatever research they're doing at the time. It's pretty fun. I like going to the seminars. There's no tests or homework. You just go in and you listen and participate, ask a question or two. But my classes, those include the convex geometry course I'm taking. There's an applied math course I'm taking called statistics. Well, it's called mathematical statistics, but everyone just calls it stats. And then the other class I'm taking, which is what I want to talk about today, is the Fourier Analysis class. Now, the guy that's teaching the Fourier Analysis class, I've had him 4 times before for Real 1, Real 2, and Complex 1 and Complex 2. He was also the one that wrote both of my qualifying exams in analysis. So I'm pretty familiar with this guy and what he expects. Of the 5 classes now that I've had with him, this one is probably my favorite. I don't know what makes it my favorite. I think it's because Fourier Analysis has some linear algebra built into it, and I remember really liking my linear algebra class. So I thought I would take just a brief moment to talk about what we've done in the class so far. It's only been 2 weeks, so we haven't done much, but we have done enough. So let's look at R2. We have a vector in R2. Now, if you remember from your linear algebra course, we can take a vector and write it as a span of 2 linear independent vectors, which in R2 forms a basis. So maybe I'll call this vector E1, and we'll call this vector E2. So that my point xy can be written as x times E1 plus y times E2. And these e's, that I can figure out what vectors they are here if I can choose them for more or less. But a lot of times people in linear algebra like to choose a basis that is orthonormal. So what does orthonormal mean? The term ortho comes from the word orthogonal, and orthogonal is just a really fancy way of saying perpendicular. Now you have to be careful with how you define perpendicular in this setting. But in R2, you can think, okay, they form a 90-degree angle there. And again, you have to be careful with how you do that because your vector space can get weird looking. So ortho means that these 2 vectors are perpendicular to one another, and normal just means that they have magnitude 1. So the length of, you can think of it that way, the length of E1 is 1, and so is that of E2. And there's and it's not necessarily unique here. So there's different orthonormal bases for R2, but the most popular one is 1, 0 and 0, 1. Pretty easy to see. We can do the same thing in R3. So my x-axis, y-axis, z-axis, this is R3. And we have a point floating here in space. So we have a vector going this way, we call E1, a vector going this way, E2, vector going this way, call it E3. And E1, 2, and 3 form an orthonormal basis for my vector space R3. So if I have x, y, z, I can write this as xe1 plus ye2 plus ze3. And again, it's not unique, but the most popular one you see all the time is your standard orthonormal basis. I think that's what it's called. I have to double check. It's been a while since I read my linear algebra book. It seems like they called it the standard orthonormal basis. And this generalizes to Rn. So if you have n-dimensional Euclidean space, which is just Rn, it's the quintessential example of a Euclidean space. we can pick a point. We have an n-tuple here, and we have E1, 2, 3, all the way up to En. And you can build it like this and figure out what it looks like pretty quickly. And like I said, it's not unique. So, for example, if I choose the standard orthonormal basis here, maybe to draw, give a picture of it with my hand, my thumb is E1, my middle finger is E2, and my index is E3. So I'm trying to form 90-degree angles here. And it's not unique because if I rotate this around and keep the angles preserved, you see my fingers don't get longer and the angle between them doesn't change. So any of these orientations that I'm making here can form an orthonormal basis in Rn, for example. So what does this have to do with Fourier analysis? It seems to me, at least within the first 2 weeks, is that if you choose specific functions, okay, I'm getting ahead of myself. If you have a function f, can you write it as a linear span of an orthonormal basis? And the basis here is made up of, functions themselves. So in order for this to make sense, you need to be able to talk about functions being orthogonal to one another, whatever that looks like, because how do you measure an angle between two functions? And they need to be normal, which means they have magnitude 1. So, the standard scalar product, we need a scalar product in order to talk about orthogonal vectors, for example. So if I have two functions f and g, the common way that we see it defined is we have integral f g bar, so it's conjugate. I think it's conjugate. You have to double check me there. Dx forms a scalar product. And typically, I think what we want to do here to make sure everything's correct is we want to integrate over an interval I, where I has measure 1. So we don't want the interval to be measured. You don't have to have the measure of the integral, or excuse me, the measure of the interval be equal to 1 if the interval is length 2 pi, which is a common length that people choose. It depends on the textbook. So I believe in this textbook, the Harmonic Analysis book by Katz-Nelson. In fact, I'll open it up here. He chooses a length of 0 to 2 pi. So it's a 2 pi periodic function. And so here he defines a norm of f to be the integral over t. So t is just the interval from 0 to 2 pi. You think of it as this, the unit circle. And he divides by 2 pi over here. So the reason he divides by 2 pi is because he wants to normalize it. And he does, once I get to this, he does that here as well. He divides by 2 pi on the outside to normalize the integral. But in my class that I'm taking, he chooses an interval of length 1, so we look at 1 periodic functions, so you don't have to divide by the 2 pi on the outside. Now, what is the system of functions that we like to use? We like to use these guys, e to the 2 pi I k x, where k is an integer. We like to use this system of functions. So the idea is that this family of functions, when substituted in here, when you look at the scalar product, they form an orthonormal system, which means that if I take the scalar product of e 2 pi I k x with e 2 pi I l x, we'll get 1 if k is not equal to L, and 0 if k is equal to L. So that this forms an orthonormal system, because we want 1 if they're different for any two choices here, and we want 0 if k is equal to L. So we only get 0 if they're the same function. So this gives us our orthonormal system, and so now we need to figure out essentially what these x's and y's are up here. So we have the e's down here, but how do we get these x's and y's? And that's more or less where the Fourier coefficients come from. So a Fourier coefficient of a function f. So let's say that f is a one periodic function and it's integrable. So it's an integrable function across my interval. We'll write it that way. Then my Fourier coefficient, which is denoted f hat k, is equal to the integral over my interval of the function fx e to the negative 2 pi I k x dx. And then if I want to write the Fourier series, which a lot of times it's written this way, in this book it's written that way, or the Katz-Nelson book, then it's written as the sum. Okay, maybe I should say that f is one periodic. Put one periodic here. Then this is equal to f hat k times e to the 2 pi I k x, and we want to sum over all integers k. Let me check this book just to make sure I didn't lie. I'm pretty sure this is what it looks like because I had to do this for a homework assignment. Let's see, Fourier's coefficients. I guess technically we don't use the equal. We write the twiddle sign here. I'll learn more in depth as to why it's the twiddle or the tilde. I have an instructor that says twiddle. So if someone can explain it in a very concise way why we use the tilde instead of the equal sign, it's something I'm still not comfortable with. Remember, it's only the second week of class. Then go ahead and put that in the comments. Okay, so let me do an example. This was a homework problem that we were given last week, and I presented this problem at the board because that's how we're graded. We present problems. So I did this one on the board. So my function fx is equal to the characteristic function from negative 1/4 to 1/4, and my interval is negative 1/2 to 1/2. My instructor likes this interval because it has length 1 and it's centered at 0, and it makes the math pretty nice. You know, in some textbooks they like to use the interval from 0 to 2 pi because it's also kind of useful. But this is the one that he chooses to use. Okay, so let me draw a picture of what the function looks like. Negative 1/2 to 1/2. Here's 0, here's 1/4 and 1/4. So it maps up to 1 on this interval and then 0 outside of it. And the idea is that f is one periodic, so that means if we go this way indefinitely, then this function just repeats so there'd be 1/2 to 3/2, it'd just look the same. And then from 3/2 to 5/2, it'd look the same. And then the same thing in the other direction. And the idea is that we want to find the Fourier coefficients of f. So that was the homework problem. The Fourier coefficients. So we want f hat k. E to the 2 pi negative 2 pi I k x dx. Okay. So what do the Fourier coefficients look like? Well, the first one that's the easiest to find is f hat of 0. So we do f hat 0 first, f hat 0, which is just the integral from negative 1/2 to 1/2 fx dx. Because if you plug in 0 for k, you'll get e to the 0, and e to the 0 is 1. So we have this. But you'll notice that f is 0 on this interval and this interval. So the integral all comes from what's happening between negative 1/4 and 1/4. And it's equal to 1 on that space. So this integral is the same as negative 1/4 to 1/4 dx. And that just gives you the length of the interval, so that's equal to 1/2. So we know what the Fourier coefficient at 0 is. Now we need to do it for k not equal to 0. So we have f hat k integral fx e negative 2 pi I k x dx. So there's a couple different ways that you can do this. Excuse me, I'm sitting on my foot. I need to fix it. Oh my God. Okay, so there's a couple different ways you can do it. There were other problems that other people did at the board in class, and it was different functions. And I noticed that they did it in a slightly different way than I did it, but it was equally correct. So the way I did it here, that was different from them. I didn't see anyone else do this, which is it is kind of amazing just how different our brains work. Like we try things different ways. But what I did was I said, okay, this is e to some imaginary number times a real number, and I know Euler's formula, so I just substituted in Euler's formula. In fact, before I do that, let me just fix this, or not fix it, but write it differently. This returns 1 if you're inside the interval here from negative a quarter to a quarter, so it really just looks like this. That's just another, I guess, simplified way of writing it. And now I'm going to apply Euler's formula. So I get integral from negative 1/4 to a quarter cosine of negative 2 pi k x dx plus I times the sine of negative 2 pi I k x, or no I here, dx. And then I use some properties that I know about sine and cosine. So sine is an odd function, which means that I can pull the negative out and put it in front of the I. And I know that cosine is an even function, so I can just drop the negative altogether. Very good. Okay, and now we make an even better observation. Sorry. So sine is an odd function, and we're integrating sine over the interval from negative 1/4 to 1/4, which is symmetric about the origin. And it doesn't matter what the inside looks like; it's still an odd function. So if you integrate an odd function over a symmetric interval, you'll always get 0. So this whole imaginary part here is equal to 0, which means that we get this guy. And that's just a normal, usual, typical integral, right? So this is equal to sine 2 pi k x divided by 2 pi k from negative 1/4 to a quarter. And so if we plug in 1/4, we will get sine of pi k over 1/2 divided by 2 pi k, subtract sine of negative pi k over 2 pi k. And do I like this or do I not like this? I mean, it's fine the way it's written here. Oh, yes, I do. Wait. Wait just a second. Yes, I do like this. Sorry. So remember, sine is an odd function, so the negative can come out. So if the negative comes out, then I'll just end up with sine pi k over 2 divided by pi k. And I skipped a few steps there, but I'll just explain. So if the negative comes out, this becomes plus, that becomes plus. And then I'll have 2 of these guys, and those 2's will cancel with this 2. So I end up with sine pi k over 2 divided by pi k. And this guy has a couple different answers. So you'll notice that if k is an even number, this is getting crowded. In fact, let's write this on a separate sheet of paper. So if we have sine of pi k over 2 divided by pi k, this is equal to 0 if k is even, not equal to 0. We've already taken care of the situation where k is equal to 0, or k is equal to 0. So we're just looking at non-zero integers k. So we get 0 there. And then for k congruent to 1 mod 4, because there's two types of odd numbers here. K is congruent to 1 mod 4 and k is congruent to 3 mod 4. So if we think back to our trigonometry, we see that if k is like 1, then you'll get this amount here. So we end up with 1 over pi k. And if k is congruent to 3 mod 4, we get the one at the bottom of the circle, so we end up with negative 1 over pi k. And so these are my possible Fourier coefficients of my function f. You know, and also 1/2. So I guess we'll write it here. So 1/2 if k is equal to 0. Obviously you can't plug in 0 here for k, because then you'll have division by 0. But the limit exists. We already calculated that it's equal to 1/2 if k is equal to 0 on the previous page. But I wanted to list it here just so that all of the Fourier coefficients are taken care of.